So the last class we looked at logic circuits. So now today we'll look at SRAM today and the next lecture. So SRAMs are basically static random cell memories, static random access memories, and the workhorse for the SRAM is the 6 transistor cell. So you have basically two inverters, N1 P1 and N2 P2, and they are connected in a feedback loop like this. And the information is basically stored in the voltages in V1 and V2. They are complementary to each other. And you can access these nodes through these pass transistors N3 and N4. So during a read, what you do is the bit line and bit line bar are pre-charged to the positive supply VDD. You turn on the word line, which activates N4 and N3. So that connects the internal loads V1 and V2 to the bit lines. So word line goes from 0 to 1, and when that happens, if we say that the node voltage at V1 is 0 and V2 is high, then you have cell current going through N3. The bit line will get discharged from N3 and the current will flow through N1 because V1 is 0. Nothing will happen on this side because V2 is already at VDD, so there is no VDS drop across this, so nothing will happen on this side, but current will flow through this. Now when current flows through this, clearly you need to have a non-zero VDS across N1. So you see V1 will go up a little bit depending on the amount of current and the resistance and so on. So this is the proper operation for a read. After the word line goes away, again everything goes back to where it was before. Now when you have a failure in read, what happens is that this node V1 goes up, and it goes up enough to essentially trip this inverter. You cause that voltage goes beyond the logic trip point of this inverter. And when that happens, V2, as V1 goes up, V2 starts falling, and if it goes beyond a certain value, V2 will just fall and V1 will take the opposite value. So when you read the cell, you flip the contents of the cell. So you have destroyed the information, content in the cell. So this is a read failure. Now as we scale the supply voltage down, typically the SRAMs, a 60 SRAM cell will work maybe 0.7, 0.8 volts in this modern processors. But here we are talking of designs where we want to get the supply voltage down to near threshold, right? Even sub threshold, 200, 300, 400, those kinds of things. And that is where SRAMs, people, it's still it's not easy to get SRAMs to work down to those voltages. Now one thing you have to remember is that when I say you can't get SRAMs down to work at those voltages, you might have a single cell in the typical corner working fine. Okay, it can probably go down all the way. But if you recall, SRAMs, you want to pack as many cells as possible because more memory is always better for your application, which means the sizes used in these transistors are all minimum size, which means they are really exposed to a lot of process variation. Smaller the size, more is the variation in the characteristics of the transistor, the threshold voltage especially. So the characteristic of the SRAM cells in an array, if you sample them, they'll be all across the process distribution. So when you have a large memory, and if you have, say, 1 million bits, if you have a few percent of bits not working properly, right? Because you see the complete distribution, right? And the tails of the distributions are the ones where you'll have problems. And if those cells fail, and you have no way of dealing with that failure. You might put in some redundancy, you might put in some correction, all of that is done to deal with that. But if failure is more than that, then again the system will not work. So because of the large number of cells involved in a memory and the small size of the cells, you have to really look at behavior of the memory cells in the tails of the distributions, phi sigma. You look at the mean plus phi sigma behavior, mean minus phi sigma behavior, and ensure that things are working properly across that larger range, right, of deviations. So that is where the difficulty comes, because of these small cells and the large variation, they don't scale down properly. So how do you fix this particular problem? It turns out that you have to pay a price to fix the problem, and the price is area. Okay, so right now, if I want the cell to work at low voltage, then we have no other way right now other than to do something to the cell to increase the cell area. So let us see what are the things people have done. Now there are two basically things. You see, there are the two steps to this failure. First step is there is some current causing a bump in the voltage here, V1. The second step is this bump in voltage causes this inverter to trip. What do we mean by trip? V1 goes and discharges V2. So there are two approaches to solve this problem, and we'll see both the approaches. One approach is to prevent V1 from going up. Second approach is prevent this inverter from tripping somehow. So first we look at the second approach. Before we get into that, how do you study these SRAMs? We have seen that how you the way you quantify the robustness of an SRAM, we also saw that in the last class with the logic cells, is to do the static noise margin analysis. So you have this SRAM, during the hold mode, these two access devices are off. During the read mode, these two are on. So these access devices, the gate is VDD, the bit lines are VDD. So you take a half cell, right? You take this half cell, which consists of this inverter and this access device. You look at the DC transfer curve between the input and output of this half cell, and you get a curve like this. Notice that this curve doesn't go all the way down to ground, because when Vi is VDD, this output doesn't go all the way to ground, because this NMOS transistor prevents it from going all the way to ground, because that is connected to bit line which is VDD. So you do it for that half cell. Similarly, you do the DC transfer curve for this other half cell, and you get this. You put them on the same graph, and then you have this butterfly diagram. So the size of the largest square you embed is defined to be the noise margin for the cell. So you can get this noise margin number, and then you can get this number across different conditions, different designs, or for the same design, different voltages, or for the same voltage, you do this noise margin number across different values for the threshold voltages sampled from the distribution, doing a Monte Carlo analysis, so you get a spread in the noise margin numbers. So one approach to solving this problem, as I said, was to actually prevent the read current from going into the cell. So the way you do that is by actually having an extra pair of transistors and having a separate bit line from which to read the cell. So you see here, this is the standard 6 transistor cell. There is a word line, the 2 bit lines. Now these 2 bit lines and this word line is now used only during the write. It's not used for the reads. So for the reads, a separate buffer, this is called the read buffer. It just consists of 2 transistors. So there is a separate read word line which turns on the read buffer's access transistor, and the internal node is connected to the gate of this transistor, and there is a read bit line. Now you still do the same thing by turning on precharging the read bit line to VDD. You do that, now the read current, the cell current flows through this buffer. It doesn't go into these nodes. So these nodes remain where they are. They don't get disturbed. So this is one approach to actually improve the read noise margin for memory cells, and this is kind of used one way which is used to help scale the supply voltage down for the memory cell. So one thing with memories is that the cell design and the cell layout both have to go hand in hand, because it's very, very critical, because you have to squeeze out the last micrometer square out of your layout. Okay, so because there's so many millions of these, you have to optimize the layout so that you get overall area savings. So anytime you make a change to the cell, you have to go back and really also pay attention to the layout. So this is the layout of the cell. So these cells, nowadays all memory cells are done in this kind of flat architecture for the layout. So you see, this is the inverter, one of the inverters, where you have an NMOS, okay, then the PMOS of the inverter, and this is the gate of the inverter. And the access device is connected here like this. So these two are the output of the inverter, which is shorted. There is a metal which is not drawn, which is not shown in this diagram, but that connects the output. This connection is basically out here in metal, and then this is connected to the NMOS, which is this access transistor, and the word line is the gate for that. The bit line is connected to the bit line, right bit line, which is connected here, goes vertically like this, right? Similarly, you have the ground for this transistor and the VDD for the PMOS transistor. If you notice out here, this ground, only half the contact is shown, because the other cell in top is reflected, mirror image of this, so that they share the ground contact. So the area is half. In terms of budget, you are sharing the area, it's half. Similarly, the bit line contact is shared. This is the other inverter, just rotated and laid out. And so all the transistors are lying horizontal. So this is also good from a perspective of matching and so on. Same orientation improves matching of transistors. In addition, it reduces the height of the cell, because the bit lines are going vertically. Smaller height means smaller capacitance. So that helps to improve the speed of the cells and also reduce the power consumption, because there are many bit lines which are switching during writes and reads. So you reduce the height and reduce the capacitance, it helps the overall power. Of course, you increase the word line length, but word line is being driven by a simple inverter. You can make it a little powerful to drive that extra load, extra wiring. And only one of the word line activates in any row, so that extra capacitance and power is not that significant. Now this is the buffer, the read buffer. So the internal node of the cell comes in and is connected to the pull down transistor here, and then this is the access transistor, and the read bit line goes vertically. Of course, you have two word lines, read word line, write word line. So all of this basically increases the area of the cell. Now, it's kind of fine to have a solution which works down at very low voltages, but it turns out that people in industry just don't like to pay, give out area. So there is, SRAM, still it's 60 cell, largely dominated by 60 cell, basically because of area. So unless it becomes a pain point where you say, look, I really, really have to run at a very low voltage. From a practical perspective, right now it is still 60 cells. So the area, that kind of shows the importance of area out here. Now to address this problem, these guys, in the next paper, we'll just see that now, looked at this problem to say, can we reduce the area of this? Instead of 80 cell, can we do something? So they essentially propose a 70 cell. Okay. The 70 cell is relying on attacking the problem in the other place. Let the V1 bump up. Let this node bump up during a read, but I'll prevent this inverter from tripping. How do you prevent this from tripping? When this bumps up, you turn on N2, and N2 is supposed to pull down V2, right? That's how it fails. But you prevent the pull down of V2 by putting another series transistor which is shut off during a read. So you still have an extra word line, but that word line is complement of the main word line. The main word line runs. Okay, so you have actually three word lines here. Word line WL and WWL are essentially connected to N4 and N3. During a write, both WL and WWL are turned on. So it's like just a standard, and WL bar is kept low. During a read, WL turns on and WL bar goes low. Right, to shut off N5. When you shut off N5, this pull down path is made open so that even if V1 bumps up, you don't have a discharge of this. So you don't trip the cell. So that's why they call this a read static noise margin free SRAM cell. This is work done by these Japanese authors, JSSE, Jan 2006. During the hold operation, when you're holding the contents of the cell, WWL is low, WL is also low, so both N4 and N3 are off. Because WL is low, WL bar is high, so this is on. So it's again, it's like an on inverter, inverter, back. So the question is, why is there an asymmetry? Why is this not here? That is because the read is only happening through one side. During a read, only WL is turned on. WWL is not turned on. So you only read from here. So if the content of the cell is 0, then the bit line is discharged. If the contents of the cell is 1, the bit line remains where it is. So even in this case and the previous case with the read buffer, these are single-ended reads compared to a 60 cell where it's a differential read. So there is another price to be paid there because it's single-ended read, the sensing and so on. You have to essentially give more. Differential operation always is more robust to noise and you can sense even smaller signals. So the question which is being asked is, because of this series stack out here, will that have a limitation on the voltage, the low voltage operation? Will that limit how low voltage I can go? And the answer is yes, because again you go back to the discussion we had in the last class and so on, is that the low voltage limit in some sense is governed by asymmetries between the PMOS and NMOS in the logic cells. And asymmetries can come due to differences in threshold voltage as well as the logic structure, series versus parallel. But that impact is very, very less. Okay, it is like, it will have an impact if you again recall, maybe 50, 100 millivolts or something. So the scaling of the voltage is not really limited by that asymmetry out here. It's really limited by the loss of noise margin due to process variation, plus minus 5 sigma. Some cells are so bad, there's so much deviation in the characteristic that that limits how low you can.
So how is write cycle?
How does write happen here? The write happens where so how does write happen? So during a write, basically you have to pull down the node which is high. So right. So if so WL and WWL both go high, right? And what happens is that the node which is high gets pulled down to ground through the access transistor, and that's how the cell writes. So, for example, if you look at V1 is high and you want to write a 0 here, V1 gets pulled to 0, right? And then V2 gets pulled high and it remains 1. Now, if V2 has to, you want to write, if V2 is high and you want to write a 0 here, V2 gets pulled low from the N4. And then basically V1 goes high because V2 goes low, P1 turns on, V1 goes low. So during the write, this is momentarily off, but it doesn't matter because this is really not doing anything for the writes into the cell. This pull down stack is not coming into the picture during a write operation because write is happening because you have been pulling down the internal load from one of the access transistors. So the question is again related to what your friend asked. The N5 being in series, how will that impact the VDD and so on? As I said, the VDD scaling, it will have some impact. It's a very, very small impact compared to the limitations of VDD coming due to process variation. And really changing these threshold voltages can change by 50 to 100 millivolt, 150 millivolts. It can change by a large amount, right? So that really causes the. So the question is now, uh, so the question which is being asked is, in a 60 SRAM cell, we had this kind of heuristic or this rule which was there that the device which is pulling down, the driver device and the access device, there is a certain relation of the drive strength. The drive strength of the driver device is 2.5 times, maybe 3 times that of the drive strength of the access device. And the reason for doing that was so that V1, say the V1 of 0, it doesn't go up by too much of a voltage. So you are controlling the voltage by sizing these relatively. Now the question is, does the same rule apply here? And the answer is, you don't have to stick to that rule anymore, because now even if this goes up, you have made this SNM free, right? So I can actually have this to be equal sizes, so you can take advantage of that to reduce the size if you want. Same for the read buffer case also. And if you see out here, they are the same size. The widths of the NMOS and PMOS are the same. I'm sorry, the NMOS of the driver and the access are the same. So this is the 7T cell. Okay. So in the 7T cell, the authors here have done the SNM analysis. I mean, basically what they do here is, this is for the case when you're holding. That means you're not reading from the cell. It's just two inverters, but there is an asymmetry now. This inverter has that extra series transistor. So you see the curves are not the same. The transfer curves are a little different. So there is an asymmetry, and this is the static noise margin. It's the lower of these two eye openings. Now when you do a read from this cell, what happens is this is off, and so the DC transfer curve of this inverter, P2 N2, because input of this inverter is V1 and the output is V2, right? So input is V1 and the output is V2, so you're looking at this curve. So the shadowed one was the curve when I'm not doing a read, and this is the thing when I'm doing a read. So when I'm doing a read, this DC transfer curve shifts to the right, because it takes much larger voltage for me to pull this thing down, because I have an off transistor in path here. So that's why the whole thing shifts to the right. So if I didn't shift it to the right, this is the DC transfer curve of this guy, this inverter. If I kept the old value, then you see that I have lost a noise margin. There's no noise margin here. But because I have put the series one, now this graph is also telling me that I pulled it out and I have a noise margin now here. I mean, some positive noise margin. Of course, what has happened is that you have a problem here on the other side. That is, when V1 is high and V2 is 0, what has happened? You have actually, during a read, VWL goes low. So you have disconnected this in some sense. And so this V2 is being held low in some sense in a dynamic fashion. For that duration, V2 is floating. Okay, so there is some negative of this approach also. Right? This internal node is floating for that duration. So if there was noise event somehow due to some capacitive coupling or something which pushes this beyond this value of SNM, then again you can have a problem with this cell, and the cell contents can get disturbed. So again, with memories, it's very important, and especially when you're scaling down to these low voltages, this Monte Carlo analysis is very important. So here what they have done is, they have done 2000 simulations. Basically, each simulation, the values used for the threshold voltages are drawn from a distribution, where there is a mean threshold voltage and the standard deviation for the threshold voltage for that Gaussian display. I assume a Gaussian distribution for each threshold voltage of each transistor. And that standard deviation sigma they have assumed to be VTH by 5. So you draw the samples from these distributions for all the 7 transistors. Then you do the DC transfer curve analysis. Then you extract the size of the squares and you look at the smaller one, and then you say, okay, and these are for case when V1 is 0 and V2 is 0. V1 is 0, you are looking at this bigger square here, V1 is 0. So there is this square, and V2 is 0, you're looking at this square. And you see that you have the distribution out here for all the 2000 points. For V1 is equal to 0. Now, because this one has become affected, you find for V2 equal to 0, some of the points are on the left of this vertical line. This is SNM is 0. SNM is negative. That means for some fraction of points, SNM is negative. So the main point I wanted to illustrate with this was that you have to do this kind of Monte Carlo analysis so that you look at what is the fraction. So this gives you it's like sampling when we do our elections, polling happens, right? Exit polls, they sample a small number of people, from there they project. There's always a margin for error with that projection, but it's kind of like that. You do 2000 simulations, and then from there you try to make sense. Okay, if this fraction of guys are off, you say this is the yield I would expect from this. So that number, what number to choose, you have to choose properly so that you have good confidence in the estimates you make. So the layout of the 7 transistor cell again is important. So this is again the 60 cell where you have these two inverters, and to see in this 60 cell, coming back to your question, the access device is a little smaller than the driver device. So this is the 60 cell, and the 70 cell basically, because there is no SNM, SNM it's Read SNM free, that's what they say. I can make all the devices to be the same size, the NMOS devices. Okay, but there is this extra device. One of them has a series NMOS, so the layout becomes like this. It's no longer rectangular layout. It has this kind of a shape, like a L. So it's not a nice shape for semiconductor layout, because when you put another cell out here, you mirror that cell, you end up with a gap. It's an ugly gap. You end up with a gap. But what is interesting is the authors have managed to somehow do something useful with the gap. So we'll see that, what they do. So what they have is, they have this, so they take these two cells, when you put this is the cell, and they mirror that cell to get two cells, and then you end up with this gap. In the gap, they fill two transistors, one PMOS, one NMOS. And that transistors they fill based on the requirements of the sensing. What is the sensing architecture? So they take a column of 8 cells, and then there are 2 columns, 8 by 2 columns. So there are 16 cells. There are 2 bit lines, BL0, BL1. For any particular bit line, this is how they sense. Imagine each of this is a cell. I mean, there are 8 cells here. We are only showing 2 of them. The read bit line is pulled down to 0 by one of the cells, whichever is turned on, right? So all the bit lines are shorted, and then there is a pre-charged transistor here, P30, which pulls up the bit line to 1. So that pre-charged transistor is also inserted in the gap. So there are basically 1, 2, 3, 4. So there are 4 gaps, okay, and you have space for embedding some transistors. So this pre-charged transistor is pushed into the gap. Now, when the bit line goes low, this inverter, this is the sensing inverter, it turns on. N11, P11 is the sensing. When it turns on, they have this global bit line. So every group of 8 cells connects to a global bit line. The global bit line is running vertically. Local bit line, global bit line. Local bit line connects 8 cells in a column. Global bit line connects all the cells, all the groups of 8 cells. So the global bit line is also pre-charged. So when this inverter goes on, if this goes to 0, this goes to 1, again global bit line will get pulled down to 0. So you are transferring the cell information from one stage to the next like that. So there is a pull down transistor for the global bit line N12. Okay, so you have P13, N11, P11, N12. In addition, you have this P12. P12 is basically what is called a keeper transistor, because when you're doing a read, okay, before doing a read, if I'm not doing anything, the pre-charge PC is kept low, so the PMOS is on, so all the local bit lines are pulled high. They're just kept high solidly. Before I do a read, if I decode my address and find that one of these 8 cells is to be accessed, I release this pre-charge so that this P13 is shut off. And if one of the cells pulls it down, good. But if the cell which I'm reading is not pulling it down because the contents of the cell is 1, then this bit line is floating for that duration. So whenever you have these, so this is like a dynamic circuit. So dynamic circuits, whenever you have the floating nodes, they are weakly connected to a VDD so that it's not fully floating. And so this P12 is a weak pull-up. Weak pull-up is such that you have to size it carefully. So design of pull-ups, weak pull-ups or weak pull-downs is a tricky problem. Okay, because you're actually, what you want is the pull-down. If there is indeed a 0 in the cell, you have that pull-down which is happening in the cell, that should overpower the weak pull-up. And you have to ensure that happens across all process, condition, etc., etc., and so on. So it's a very difficult and tricky design to make it work. Especially in deep submicron itself is a problem at high voltages, and that is why people largely have moved away from these what are called dynamic circuits in deep submicron, because process variations makes it very difficult to design your pull up and pull down, because it's like ratioing, right? You have to get the sizes correctly and it has to work across all process variations and so on. And it will become even more problematic in the sub-threshold. But when you have such large number of devices and you have to, essentially it's an OR functionality, right? It's like a MUX functionality. So you can't have a full static CMOS implementation of this MUX because you just blow up the area. So you have to go do it like this. You have to have some weak pull-up. But this is an important failure point, I think, where you have to kind of pay attention and see how to make it work. So you have all these transistors, and then this is the transistor for the right. So all these transistors are very cleverly embedded in these gaps. So Japanese are known for miniaturization, right? So they have very nicely folded things, origami, everything in the gap and hidden everything. So everything fits nicely. At the group of 8, it looks like a nice rectangular block. So you see clock goes high, word line bar comes low and word line goes high, and then the bit line discharges. This is the bit line. And then when the bit line discharges, the global bit line discharges. And then the output also discharges. So clock high to output, this is the access time. So one important thing here is that if V2 was low, if V1 was high and V2 was low, and when I'm reading the cell, WL bar is low, so this is disconnected. So for that duration, V2 is floating, right? For the duration of the word line high, V2 is floating if V2 was a 0 value. So it puts a timing constraint, that is the overall delay of the bit line should be less than the word line pulse width, should be less than the retention time of V2. So that is a constraint. So they ensure that the word line pulse width, you can't just ignore the word line. You just, you can't say, look, I'm turning on the word line and I read the cell, I'm done. I'll disconnect the word line at some later point before the next cycle. You cannot do that, because when the word line is high, that time the cell V2 could be floating and it is exposed to coupling, noise, etc., and it can trip it. So you have to manage the width of the word line. As soon as your job is done, the word line, you have read the cell, you have to shut off the word line. Right? So that they have some technique to do that, which you can read in the paper. Basically, you have to manage the pulse width. So, what does this buy you, right? So if you had 8 cells per bit line, as they have, then a 6 transistor cell structure has area occupied by the cells here, and this is the area occupied by the sensing circuit. When you go to 70 cell, you have additional 11%, whereas an 80 cell is an additional I mean, it's 15%, or rather, it's 15% less the 70 than compared to the 80. So this was the ISO configuration. That means the same configuration across. They are just doing a comparative study of the area. Here, what they are saying is, let me keep the speeds the same. When they do that, they claim that the 70 cell is because. So what happens is that here you see this plus 13%. The area of the memory is plus 13%, but the overall area increases only by 11%. Here, the area of the memory goes up by plus 13%, the same because the cell is the same. But the sensing area, because there are 4 cells per bit line, there are more inverters, right? The global word line in this NMOS transistor. See, there is this NMOS transistor, right? There are more of them for the 60 cell. As you partition the bit lines more, as you make the local bit lines smaller and smaller, there are more partitions. So more of these overhead transistors coming, the area overhead goes up. That's what is happening. The area overhead is more. So what they say is that if I want to keep the speed the same, I have to reduce the number of cells in the bit line for the 60. And when I do that, the area actually goes up of the 60 approach. So their 70 approach is better compared to the 60 and the 80. So that is what basically they say. Now, one thing is that just because it's published in a paper doesn't mean it's gospel truth or that is the way to do things. So that is one thing you have to keep in mind. I'm not saying there's anything wrong with what they're saying. The only problem is they are comparing situations where you have 4 cells, 8 cells, right? Now that is heavily partitioned already. So whereas if you see currently the memories and macros which you use, you don't do such heavy partitioning. You will have 64, 128 cells and so on. So and that is where one of the problem comes with this sub-threshold SRAM design, where you are really to pull the voltage down. You are doing this heavy partitioning. There is a reason for doing this heavy partitioning, and that is basically if you go back out here, when I have a column of cells, remember that in a bit line, I'm accessing one of the memory cells, but the other cells are off. But the other cells, the access transistor is connected to the bit line. So you will have leakage currents. If you recall, it's really a mux. If you recall a discussion about mux, you want to keep the fan-in of a mux small. Whereas in a memory cell, if I have a single column in 64 or 128, which is what is done in super threshold, you have an on device, which is an access device, which is also in sub-threshold, and you have all the off transistors, which are also in sub-threshold. So you can end up with failure. You will not be, the on cell will not be able to overcome the leakage of all the other off cells. And that is the reason why you have to go to more extreme partitioning as you go down to the supply voltages. It's the same argument we said for muxing. We want to keep the fan-in small of a mux. The same thing. You want to keep the mux thing small. And when you do that, naturally you pay the price for increasing the area. So that is a problem. So now to deal with that problem, these authors propose a different approach. They say, okay, they increase the size. So to deal with the area overhead problem, they increase the number of transistors in the cell. It's kind of contrary to what you would expect. So we went from 60 to 80. Then those guys said, Takeda said, oh, 80 is too large, let me get to 70. But then these guys are saying, let's go to 10T. Now, why is it that they are saying, let's go to 10T? And it's really coming down from the observation that, okay, you have a cell and you increase the area of the cell, but can I recover the area by having more cells in a column? Can I go back to a condition where I have more cells in a column? Typically, if you see right now in super threshold operation, as I said, the memories will have by 64 or by 128 or by 256 configuration. Not by 2. The column could be 64 or 128 or 256 and so on. So there are many cells in the column. So when I go to this sub-threshold and I go down to 8 cells or 4 cells per column, it's just not going to work. The area overhead is just going to be enormous. So that is another, that is a problem. So here what they are saying is, let us try to keep the area small by increasing the number of cells in a column. Let's go back to the old way of 64 cells per column or 128 cells per column and so on. And can we address the problem of leakage? The off leakage from the cells which are not connected. So that is why they have this structure. So the read buffer, if you see read word line and M7, M8 and M7 are from the same as in the 80 cell. Right? There is a separate read buffer. But in addition, they have a transistor M10. M10 is there so that when read word line is 0, that means the cell which is not accessed, I don't pull down the current in the bit line. Now, what is the problem in the for the leakage? Right? The problem is if I have say 256 cells in my column, one of the cells, let us say, is supposed to pull down the bit line, or not pull down the bit line. Maybe the cell has a read data of 1. That means it's not supposed to pull down the bit line. But let us say the remaining 255 cells have the opposite data in them, and the leakage through them then can overpower and actually pull down the bit line, and you will think that the value is 0, but it's really the sum of leakages from all the other guys, right? So that will lead to a wrong operation. So that is why they want to address the problem of leakage by having M10, another transistor M10 in series. So you have two transistors M7 and M8. In addition, they have M10. So M10 is basically RWL is connected to both. So when RWL is 0, that means the cell is not accessed. You have two series of transistors. This could be on because we don't know. The case is QB is 1, so M7 is on, right? And but then you have two of them in off condition. So one of the ways to reduce leakage is to actually do series stacking. When you have series stacking, it helps to reduce leakage quite significantly. In addition, what they do is they have put a PMOS M9. The purpose of PMOS M9 is when QB is 1, okay, that is the case we are concerned about. M7 is turned on, M7 is on, but M10 is off. But they are still concerned, they don't want this node voltage to eventually drift down to 0. So they put M9. So M9 is also off because QB is 1, M7 is on, M9 is off. But the least leakage, off leakage through M9 is helping prevent this internal node from going low too much. So they want to keep this internal node here close to VDD. When QB is 0, it will be at VDD. So there is no problem because M9 is on. When QB is not 0, QB is 1, it will not be exactly at VDD, but it will not be at ground also. So that plus the series stacking helps to reduce the leakage from here, and so they are able to now stack many cells. In fact, if you read the paper, you will see that they also go to 1,000 cells and so on. And when you do that, what they claim is that they can recover the area lost by going to 10 cell.
So here series stacking, you can use a one transistor and it's double the length. It's near the threshold.
So the question is basically, why not use one transistor with double the length? Now you have to be a little careful because of the impact of length on the threshold voltage. So you have to keep all that into account and then do it. You can have a short channel effect which helps increasing the channel and increases the threshold. But if you have reverse short channel effect, it can go the other way. So you have to kind of do things, keeping all those things, take all those things into account when you do this side. Any other questions? Pardon? The question is, what is the role of M9? The role of M9 is to keep this node close to VDD. This node, because when this node is close to VDD and when I'm off, then I won't have much leakage. M8 will not discharge. That is what M9 does. One, M9 is off, but remember all these are leaking in a subthreshold. Even M9 will be leaking. Small leakage, it will help, at least it will prevent this from going all the way to ground. It will keep it at some value above ground. Absolutely. So it is not like precisely controlled. The exact value where it is will vary. Correct. So then if there's not much leakage, then this can go all the way down to ground. Absolutely right. Yes. Now the thing is that because of the series, that's when the series stacking helps to. So it's like there are two things which are being done. P9, M9 is there and M10 has been added. Both have been added to help reduce the amount of leakage. But the amount of reduction itself depends on the, yeah.
In the graph, when we compared 60 and 70, the previous graph, why did we take 4 cells for decline for 60?
So what they are doing is this one is um, giving them the same speed as that of the 70 and 80. So the 60 cells pulled on current seems to be lower than that for 70 and 80. So because of that, um, they are because you have the 60 here, and the 60 access device is narrower compared to the 70 or the 80. So the cell current also is lower for the 60. So the speed is lower. If I want to recover the speed, if my drive strength is small, I have to reduce the capacitance. That means I have to have smaller cells. So that is why ISO speed configuration with the 60, they have to use smaller local bit lengths. Okay, we'll continue again in the next class and look at writes. What can be done? Why will writes fail? And what is done to prevent that from happening?